So now, I'm going to do another long step-by-step video, but this one warrants it a bit more than the last couple I did. But in any case, we have an LM393 comparator right here. That's the integrated circuit. It's not an op-amp, even though it looks the same. You know, it's in the same packaging that you see when you have an op-amp or a comparator in a through-hole package right there. And there's other circuitry you can do as well. And yeah, blue LEDs kind of hit in right there. There we go. Now we can see it better. So we're going to do a step-by-step build of this, so don't try to focus too much on seeing how I wired that up. This is the circuitry that is right there. So you should be able to build it just from that. That's what I just did, of course. And this is an old diagram. And so, of course, I made the diagram long before I put together the circuit. And usually it's easier to make a diagram before you build a circuit, unless you're just kind of modifying something you're familiar with. But in any case, we got high or low. All this is a comparator. It has the same symbol as an op amp. You may or may not see the power pins on the symbol. Here I did not add it, but you always got to power the integrated circuit. But we have an output. Technically it goes high or low, but all it can do is connect to ground through a transistor really well. It cannot connect to the positive supply at all. That's why we have the pull-up resistor. First off, we need the pull-up resistor to turn the NPN bipolar junction transistor on, and also pull-up resistor helps turn off the PNP bipolar junction transistor when we have a high output, which is technically just off right there. So pretty much every circuit I see that has a comparator integrated circuit with an open collector or open drain is another version. That means all it can do is connect to ground. So if you see open when it comes to an output, there's a good chance that's all it does is connect to ground in one form or another. I almost always see a pull-up resistor. So now we're going to wire this up, and prior to this I made a number of mistakes. I'm refilming this, and I think I'm just refilming this once, but before I even started filming, I should say, I had the transistors in the wrong spot, which caused kind of a problem. But we're not going to dwell on that too much. Just I'm going to mention mistakes I made earlier. So first off, doesn't matter which transistor we grab right there. So this is a 2N3904. I did not write the part number down there. Usually I write a part number for one that will work. I accidentally put PNP when I was drawing this. But this is an NPN bipolar junction transistor, 2N3904. And you can look at the data sheet for what those other letters and numbers mean, but the main thing is it's a 2N3904. Also, the data sheet you look at will be from a particular manufacturer, and you know, this is probably a generic one, a knockoff one, so who knows how accurate that even is. But in any case, we got the emitter to ground right there. Emitter is the left pin. If it starts with 2N, that is probably the pin layout right there. That's the pin layout I always see, whether it's NPN or PNP, if it starts with 2N and it's a bipolar junction transistor. So we have the LED short lead, the cathode. It's going to go to the collector right there because that heads to ground. Long lead, the anode, we're going to go up one spot. And here's the mistake that I made while I was filming this earlier. This is a 220 ohm resistor right there going to the positive supply. I had it to the negative supply. So when the transistor turned on, the LED didn't turn on. It took me quite a while to realize where I made that mistake right there. So first thing you do, if part of a circuit is not working as you expect it to, make sure it is all wired properly. You can also get out the multimeter, measure voltages, make sure it's getting the voltage that it is supposed to have. But that's the main thing. Probably most common thing is putting the resistor in the wrong spot, in this case, putting a component in the wrong spot, or putting the LED in backwards. LEDs don't light up if you put them in backwards. So we have the 2N3906 right there. Again, you can look at the part number, 2N3906. I can easily see this with the bare eye, but you know, some of them they're kind of rubbed down. You don't see them too well, and also, you know, some of them maybe you just don't see as well either. So yeah, we got the emitter now. So it was the left pin, now it's the top pin right there. That's going to the positive supply. So I like to have the whatever goes directly to the supply rail already plugged into the board right there. And then I can use that to guide the right pin to make that connection. So emitter to the positive supply. When you're doing it to a switch, the emitter goes to the supply rail. PNP to the positive supply, NPN to the negative supply. That's the way that they're made. And then we are going to swap the position of the LED and the 1K resistor right there. So doesn't matter what order they're in, but again, the LED has to be connected in the right way. So long lead the anode to the collector, short lead the cathode is going to head to ground, but it's going to go through ground through a 1000 ohm resistor. The reason why I'm using such a high value resistor for the blue LED is that it's really bright even at low current, you know, like 2-3 milliamps of current or so. Red LED needs about 10 to 15 milliamps of current to be really bright. So we have a lower value resistor. A lot of outputs can sink and source current both, and they don't source current as well, which I usually use to light the red LED. So again, you want a lower value resistor to overcome that as well. But in this case, we don't have that problem, but still, the LEDs are going to be about the same brightness in both these cases, even though this is going to have, you know, close to 4 times as much current going through it, approximately 3 or 4 times. So let's get back to this. We have the output needs a pull-up resistor, and then it needs to send or receive current from the transistors. So let's do the 10K resistors first. Transistors just need a little bit of current when it comes to the base and emitter. In this case, emitter base there, because current's flowing in opposite direction between the two of them. And this was one thing I did wrong. One of these resistors I put to, I believe, the collector of that one instead of the base. So I'm being very careful that I plug it into the right spot right there. So I noticed things weren't working properly when I tested the circuit, and that was one of the problems. And then that resistor also was connected to a wrong spot. So being careful that I wired this up correctly. And we will also do the pull-up resistor. Before we do though, I still have the alligator clips attached to here. And generally I try to remove them before I do a step-by-step build. But as long as I turn the power off, then we should be fine. Right there, I'll come back there. Power is off. If I turn the power on, let's see what happens. There we go. We got a blue LED lit up. We're not giving a signal. That's what's preferred. Remember, the output can connect to ground, which would turn on that transistor, so that would light up. But yeah, apparently we don't have stray signals strong enough to turn that one on, which makes sense. The stray signals would affect the output more. So, in any case, but we don't have the pull-up resistor, so that LED wouldn't be able to turn on. Anyways, let's add the pull-up resistor. I'll get that out of the way so we can see the schematic, what I'm doing. We don't, yeah, we have that, but the inputs aren't wired up to anything. So pull-up resistor, now you're going to see, yeah, it looks like it's bouncing back and forth right there. So, in any case, I'm going to turn the power off, and then we're going to remove the inputs right there. So yeah, if you see something like that, that's a good indication you got something wrong with your inputs, which we do. We don't have them wired up at all. So let's get to them, and hopefully, you know, you already know this, because I do a lot of op-amp videos. A lot of people do op-amp and comparator videos where they talk about this part of the wiring up. But in any case, we got the LM393. It's important that you look at this. Our trim pot, our variable voltage, is going to go to the non-inverting input plus, which is lower on the schematic. It's also lower on the physical component. Make sure, because schematics, maybe they'll put the plus above the minus, but on the physical component, minus is always above plus. So wherever minus is, that's where you have to connect the components that go to minus. If it's higher on the schematic, doesn't matter, then you got to make it higher on the physical component. I meant to say if it's lower on the schematic, doesn't matter. It's got to be higher on the physical component. Got to wire them to the right input. Otherwise, you'll notice either it won't work or it'll work the opposite of what you were expecting. So, a couple of 10K resistors. Main thing is they're equal value resistors, and therefore the inputs don't let current go in or out. That would throw off the voltage, but otherwise we'll have half of the supply voltage, somewhere really close to about 2.5 volts at the inverting input. And as long as we keep 5 volts at the supply, if the supply voltage changes, then the half voltage, of course, will also change. It'll be half. So right there, pretty simple. We have one to the positive supply, the one that's upper, and then I usually tuck the one to the negative supply in between them, the two leads of the other one right there. So these two can touch. That's all one connection. You want to make sure that the pin going directly to the negative supply is not touching any of the other pins going directly to the positive supply. that would be a short circuit between a negative and positive supply. So we're a little cramped there. It's harder to see the gap on the camera than in person. There is a bit of a gap. But in any case, we will do our trim pot again. This is first off, it's a variable resistor. The 2 pins, these are nice. These particular trim pots, if you see, are really nice. They just have little metal pins on there. So if you're going to be building a lot of breadboard circuits, I recommend looking for these. Other trim pots have wider, I don't think you call them pins, wider metal terminals that they will like fit in the breadboard. You might want to like twist them so they're facing like left and right instead of up and down. But these little metal pins really fit in. And the 2 end ones, there's a 1000 ohm resistive element that goes from one to the other. It's roundish in shape. And then a wiper that slides across there, you know, as you spin. It's this. And it's a single turn, goes from one corner to the other, but cannot spin multiple times. There's other ones that spin multiple times. It slowly moves the wiper along the resistive element. And so those are harder to pinpoint exactly where you're pointing at unless you're measuring it or observing the effects in some way. And these slots are not just kind of accepting. I feel some fighting going on. So I don't want to damage the slots. So make sure it just slides in smoothly and you don't force it into a metal that is fighting back, because that could bend the metal. So yeah, then we go to the plus input right there. And now that should be everything. And so let's get the power supply over, and power supply is off. You should have it off until you're completely ready to power everything, just in case we accidentally short something or whatever. But yeah, there we go. We got plugged in. Turn on. Hopefully I made no mistakes this time. So it should be a high enough input voltage right now to set the output high, even though we're about halfway. So again, there's about 5,000 ohms of resistance to the positive supply, about 5,000 ohms of resistance to the negative supply, but we're probably slightly closer to the positive supply right there. So it's going to be somewhere close to 2.5 volts, probably a little bit above. If I turn this down just a little bit, then we should get a low output right there. And I did go slow enough this time where I saw something kind of, it didn't jump right from high to low, but there we go. If I really go like halfway, then we can get both of them. But there you can see. Now we pretty much got one or the other. We could use positive feedback in order to overcome that real little narrow middle ground ridge if we needed to. So that's called Schmitt trigger. That's usually the most useful circuit when you got just a very slowly changing voltage like that. But for our demonstration purposes, that's just another layer of confusion if this is completely new to you. Once you have a grasp of comparator circuits, definitely get familiar with the Schmitt trigger circuit. It won't be confusing then, but it might be a little confusing talking about feedback when you're not even fully comfortable with the comparator circuit. Not a complex circuit or anything, but when you're brand new to electronics, everything is confusing. These components don't give you indication of what they do just by looking at them. They're just plastic here and whatever that is, ceramic or whatever, and then like silicon and plastic over there. That's all it is. You don't know what it is until you experiment with them and stuff and read about them and all that. So any case, yeah, I think that was pretty much everything for building the circuit. So now, we got the multimeter. We've been talking a lot about voltages. Of course, there's currents involved, resistance and all that. But the main things for this particular circuit is the voltages that we're working with. We got the 2 input voltages, whatever the output voltage is, thanks to the pull-up resistor, or whether it's low connected to ground, and so on. Also, we want the full supply voltage across the loads for whatever reason, whenever we're using transistors, when we also have the output of an integrated circuit. So, any case, this particular meter, I only have to remove the red probe for high current. Black probe is always calm, no matter what. Other meters may have, a different setup right there, but usually not too hard to figure out. Now, to take our measurements, the probes push on components and stuff, which will actually alter the measurements, because it will alter how well it's connecting and stuff. And also I get to keep my hands free and everything and out of the way if I just take these alligator clips, which I just crimped onto a normal. The other end looks like this. I just squeezed on the alligator clip with a pair of pliers right there. Pretty simple, but seemed to make a pretty effective connection right there. So first off, we will look at our signal voltage, the trim pot right there. So it's 2.9, that's above about 2.5. We're not going to get exact numbers right here, but you know, it's high enough voltage, and I'm trying not to touch the components there with the jumper, because that seems to affect it a bit as well. But somewhere around about 2.5 volts. So you can see they're both kind of lit up, but we go a little bit lower, and there you can see that the blue LED lights up right there. So we kind of got a middle ground region, and the multimeter might affect it a little bit too. It's headed to ground, and we're measuring our signal voltage right there. So it may kind of alter things a little bit. But yeah, there you can see, well above 2.5 high, well above 2.4, or about 2.5, I mean, low. And of course, the voltage we're comparing them with is the inverting input right there, and it's pretty spot on 2.5 right there. And before I was kind of rubbing that wire against them. I think that was making it change a bit. I was filming this earlier, and I was getting all kinds of erratic numbers. But it looks like once I move this jumper far enough away where it's not bumping anything, again, we got, you know, above about 2.5 high, and then below 2.5 low. This is our reference voltage. It does not change. It stays about 2.5. We do see a little bit of change. We may be able to stabilize that with some capacitors and stuff. Something to be aware of if you need even more stabilization. Also, positive feedback overcomes like the slight changes you may get with your reference voltage. Doesn't matter. You got the output going to the plus input, a high value resistor. That helps to make a higher voltage even higher, and then a lower voltage even lower when it comes to your signal voltage. So now, the output voltage. I have not planned to look at that yet. Output's going to stay low because you don't need a pull-up resistor to go low. But I'm going to move that over and then slide in between the pull-up resistor and our two resistors going to the transistor. So there you can see, pretty close to 0 volts right there. And just needs to be enough to turn the PNP bipolar junction on completely. And then I go the other way, go high enough voltage. And there you can see, again, a little bit shy of the 5 volts right there, which makes sense. We got a resistor. It's a resistor base, so we're going to get that voltage divider stuff. But again, it just needs to turn on the NPN bipolar junction transistor enough to turn it fully on. So I was hoping for even closer to 0 volts right there. But again, we're using it to switch transistors. These integrated circuits, I don't see them being used to power loads directly. They seem to be sending signals to other stuff, and those signals can be close to the negative supply or close to the positive supply, high or low. It's plenty fine. So now, the final voltage measurement that we're going to look at. So this is usually, when you see something like this, usually the concern is that the integrated circuit can't power the load directly. That's usually why you got the transistor. So we're going to go across the red LED right there, and when the transistor turns on, we see the LED lit on. That's when we want really close to 5 volts. So that'll be across the red LED and the 220 ohm resistor right there. That's usually the main concern you got when you got transistors, although I make a demonstration circuit. So we're not getting the full 5 volts, although probably not making full 5 volts to the rail, but pretty close right there. So a lot better than what the integrated circuit could do by itself. We can look at what the voltage is that's actually making it there. There you can see it's also a little bit low right there. So we're not dropping a ton with the transistor. Now we are going to go over to the blue LED. So again, its anode is to the collector of the PNP bipolar junction transistor. So that's the more positive side that we're going to measure, and the other jumper is to the negative supply right there. So yeah, we can just end it there. It's making a connection there, although it'd probably be more accurate measurement if we go right to where the resistor is. So I'll do that, even though it took a little bit of time to move that over. There we go. So yeah, we should be pretty much almost directly across to them. Of course, they're off. There's the transistor's not on, so there's not going to be a voltage difference until I lower the trim pot enough. And there you can see, again, we got our about 4.9 whatever across the LED. Basically the full supply voltage. There's a tiny bit of loss, but nowhere near the loss we would get if we're trying to power directly from the output of even op amps that can provide, you know, like up to 20 milliamps of current sinking or sourcing. Usually you lose even more voltage than this. So for those, if you need a lot more of the supply voltage across the load, you would still switch a transistor. That's the main thing. But for beginner learning electronics videos, the main thing is just understanding the concepts of everything going on. Not so much how you can make a practical circuit with that. Making the practical circuits a useful circuit generally comes after that. You got to understand all the basics before you can understand how you can combine them and make practical circuits. So in any case, that's it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.